Hello, everybody. I again welcome you to the third day of the Young Scientist Symposium. We have a great line of speakers for today, and we will also again have a poster session in the evening, depending whether you are in the European time zone. The first session for today is dedicated to theory mostly. And the topic revolves around photoionization induced dynamics. And our first speaker is Professor Piero Decleva from the University of Trieste, and he will be talking on advances in the simulation of molecular ionization processes. Professor Decleva is at the IOM-CNR and at the DSCF of University of Trieste, and he became a lecturer in theoretical chemistry in 1976. And an associate professor of quantum chemistry from 1982 to 1994. And following that, he is a full professor of chemical physics up to present day. He is the author for more than 300 research papers in international journals, and his research covers theoretical description of many body effects and electron cross-sections in molecular photoionization. And he has really a lot of collaborations with leading both experimental as well as theoretical groups. A large molecular code for the calculation of dynamical photoionization observables has been developed in Trieste, mostly under his group called Tyresia, which emphasizes on ultra-short time-dependent phenomena and strong field ionizations. Now I request Piero to start his presentation.
Thank you, Torsha. Okay, maybe you see me, hopefully.
Yes, we do.
Okay, try this screen. Okay, is that okay? Do you see?
We see, but maybe you can go to the presentation mode.
Yeah. Sorry, how do I do that? Blah, blah, blah.
You did it just a few seconds. It's a PDF, so if you...
full screen, just full screen.
Yeah.
Full screen like that. Okay.
Yes, that's
perfect.
Okay. Fine. So, good morning to everybody. Nice to be here, and thank you for the invitation. I chose, just since there are many younger people, to present basically the methodology with a few applications. Oh my, this doesn't work now. Okay. Well, say most of the experiments we are interested in involve pulses of high energy radiation. So the main outcome is electron emission. And in fact, the detection of electron is one of the most important probes of such processes. So let me start with the simplest process, which is one photon photoionization. A photon hits a molecule, kicks out an electron with a given momentum, and leaves behind a molecular ion in a well-defined quantum state. Okay, however, if you have a more complicated process that involves complicated pulses and so on, that changes the excitation mechanism, but remind that the final state is always the same. Also, this is limited to just one photon, one electron emission, but that covers the vast majority of processes. Still, there is an amazing variety of processes because you have very many channels available that can mix. And in fact, a theoretical description typically starts from, say, choosing the dominant channel and then carefully introduce coupling with the one that are most relevant, and in particular if they are seen in the experiment. So the triviality, but not always so trivial, we need bound state. I will just talk of the electronic part and say that, for instance, for an ionic state with a single hole, you can just describe it as a single state, a single Slater determinant. And believe me, this is generally not too bad a description, unless you go very down in the valence shell. But of course, you can improve by mixing some such a determinant combination, and you have correlation in the bound states. Okay, just remind me, because it's an old knowledge that I think has been a bit lost. Correlation comes out in two flavors. One is the obvious so-called dynamical correlation, which is due to instantaneous electron-electron interaction and the cusp in the wave function. The other is tied to degeneracy. For instance, when you stretch a chemical bond, then say single determinant doesn't describe it well because of degeneracy between bonding and antibonding, and they are quite different. Now, our first starting point is Hartree Fock, single determinant, or DFT, which is still basically single determinant, but by the magic of density functional, typically performs a bit better than Hartree Fock. Then, of course, you can have CI, the modern CAS type CI plus optimization of the orbital, plus perturbative correction for the dynamical correlation, or for the excited and ionized states, also green function or propagator methods like ABCN, IOM-CC, and so on. And by the way, CI type approaches are good for the non-dynamical, but not so good for the dynamical. On the other hand, say typical coupled cluster and so on are strong for the dynamical, but not so good sometimes for the non-dynamical. So there can be problems. Okay, continuum states. You start with the product of an ionic state, a target state, and the continuum orbitals. And that already describes the vast majority of structures in the spectra, oscillations, angular distributions, and so on. Electrons talk to each other, however, so there can be coupling with other channels leading to different ionization, or if there are degenerate bound state at this energy, they can mix, giving autoionization resonances typically restricted to a very small energy interval. And again, you can start your description with HF or DFT. Then the lowest level, including coupling between channel, is CI with the singles, or TD-DFT in the DFT environment. And if you couple ab initio all the channels, you have a close coupling, which is in principle accurate as you want. And there are now say a revival of those methods. The R matrix, XChem developed in Madrid, Armin Skrinzi has developed another one, and so on. It's an open question, at least to my knowledge, if green functions approaches can treat the continuum, in the sense that there are problems with the boundary condition, but still Marco Uberti has developed a hybrid ADC approach, at least for the time propagation. Well, of course, in all description of paramount importance is the description of the continuum electron. One can start with analytic description with the plane of Coulomb waves, perhaps orthogonalized, say at not too high energy. These, frankly, are rather poor descriptions, but they can be used as a basis, like François Remarque showed. You can do one center expansion in a grid, which is perfectly fine for small systems, but then converges very slowly for larger systems. There is the continuum multiple scattering, makes approximation to the potential and still uses a grid. Cartesian grids are used for wave packet propagation, but not much for the continuum. However, the Japanese group of Ishikawa has made a great advances with that. And the best, in my opinion, is multi-center basis set. So I jump straight to our own choice, which employs B-splines as the radial part of our basis times spherical harmonics. B-splines are made of polynomial pieces. They are zero outside the small interval, so they keep linear independence very well. And you just replicate to get a representation as dense as you want. Now, again, there may be different choices. Ours is full B-splines, both for a larger center, a larger range, one center, and expansions around the nuclei. In our matrix or XChem, they use a hybrid approach, GTOs for the inner part and the B-spline for the long range. And our basis is fully symmetry adapted. This is something that is relatively rare, but if there is a high symmetry, gives a huge, say, reduction in computational cost, and also a cleaner interpretation. Well, so I could boast that for the continuum, the solution is totally satisfactory, can cover all ranges. Now, of course, the problem is in the description of the many particle systems. We started at the lowest order, which is the DFT correspondence to Hartree-Fock static exchange. So you have a one particle Hamiltonian, the so-called Consham in DFT, which is defined by the ground state density. And we can get eigenvectors, even fully diagonalize this one particle Hamiltonian. And we have our approach for getting eigenvectors in the continuum, but there are others that work as fine as ours. So the full wave functions are Slater determinants with the bound state or one continuum orbital, and the transition matrix element boils down to a single particle transition matrix. I use here always the dipole operator, but we have also the first order non-dipoles. And that works decently. It's not extremely accurate, of course, but decent for photoionization from closed shell systems to primary ionic states. This is a bit restricted if you want, but still covers the vast majority of processes. One can improve by coupling those single excitation channels, and you get TD-DFT. I will not go into the details because they are long to explain. Just to say that we compute in the same basis the so-called effective potential, which is the sum of the driving field and the response of the system. And in the end, it boils down to substitute in the transition matrix elements in place of the bare dipole operator, this effective potential. Now, there is still another possibility to improve, which is describing the bound states in a correlated way, arbitrarily highly correlated. That comes out from the fact that when you consider the transition dipole between initial state and the product final state, it again reduces to a one particle transition like before, but instead of the initial orbital, you have the so-called Dyson orbital, which is one particle orbital and is completely computed purely in terms of the bound states. I have here the expressions, but it's not now, it's the concept that interests me. So those are now computable with many quantum chemistry codes. There is also another piece which is called the conjugate Dyson, which is generally omitted because it was shown to be very small. For instance, at the Hartree-Fokker DFT, this would be rigorously zero. However, say Bruno Tenorio mentioned it, there are now situations in which it's becoming important and we are considering, but this is really an aside. Again, the important thing is that the transition matrices that we are interested now are as before, but in place of our DFT orbitals, we use the Dyson orbitals. This has two advantages. One, that it's still computationally cheap, apart from the added calculation of Dysons, which is not that heavy. The rest is exactly as before, and allows treatment of processes in which the bound state are multi-electronic, so ionization from excited state, ionization to ionic state with multi-electron excitations. Okay, I'll skip this. Is anybody interested in the computational efficiency? Just to say that the algorithms are very simple, so they parallelized very well, and say at least at the DFT level, it's really very fast. Now, a bunch of examples. This is C60, which I went through several times during the years. You can see this panel. The blue is the experimental total cross-section, red is DFT, and it fits very well the experiment. Black is pure DFT, and as you can see, is a bit lower, but nothing dramatically different. I mentioned that because in models, so-called Jellium models, which employ an effective spherical potential, they see, going from DFT to DFT, a dramatic increase order of magnitudes of the cross sections in this region. And that has created what I consider a myth in the literature, that in C60 there are giant response effects, so-called plasmon resonances, that say these calculations, which are more accurate, disprove in a way. Okay, if you look on the large energy scale, you find that after the first 50, 70 electron volts, the cross-section is basically the sum of 63 atom cross-section. You can see here the comparison. This was more or less known, but we have computed up to 1 kilo electron volts here. However, there are still interesting features. In the low energy region, there are many, many spikes. In TD-DFT, these are also due to autoionizations. Those will be washed out when you add nuclear motion, so you don't really see in the experiment. But just to check that we hadn't numerical noise, this is a DFT very fine energy scan of the cross-section in the first 20 eV. say, from the opening. And you can see this large number of very sharp resonances, and you can follow the profiles, so they are not numerical artifacts. But the DFT describes only shape resonances. So this is a very strange thing I've never seen in other systems. Means that in the case of C60, there are some kind of virtual states, very, very localized, that show up, but it's not auto-ionization, it's just within the same channel. And okay, characterizing that might be, say, a task that I will look at. Even the high energy cross-section is not completely flat. However, if one looks in detail, here is homoionization. There are oscillations, longer range oscillations that have been known for many years. They are of geometrical nature. In fact, you can see DFT and TD-DFT are very close, and they reproduce also very closely the experiment. Now, let me jump to a totally different aspect. This nice colored plot is a result of a recent work done with our colleagues in Zagreb, Nadia Doslic, Thomas Pitesha, and Marin, and they did a beautiful work. This is pump probe, simulated, say, the dynamics with their surface hopping approach. And we joined for the calculation of time-resolved photoelectron spectra. And okay, this is pyrazine, which is continually investigated. Even very recently, we heard a communication about transient core absorption. And okay, this is our simulated cross-section, time-dependent, and this is the experiment, superb experiment by the group of Professor Suzuki. And here is the angular distribution. And say the agreement is quite satisfactory. I would say we have some problem here, but this is due that here we are at a very low kinetic energy, and DFT is not that good at such low energies. Okay, the whole thing has many aspects that I will not touch, but I want just to stress that there was one disappointment. Now it is maintained, say, there is different opinions in the literature, but also the last core photoabsorption seemed to confirm that in the dynamics there is also not only the first and the third singlet state involved, but during the decay through intersections, also the AU state is populated. However, say, we didn't find a clear signature of these A2 states in the photoelectron spectra, because, say, each of them decays to several ionic states, and basically calculated emission from S1 and from S2 mostly overlapped. However, I must say that, okay, this was confined to very low kinetic energy because of the laser excitation. But of course, with free electron lasers, for instance, or high harmonic generation, you could go to higher energies, and the simulation can cover, actually we have those data, explore a range of experimental possibilities, and maybe point out some in which say, a signature of the different states one is interested can become more prominent. Also, I just added here, this again is loosely connected. These are MMF paths recently measured by Giuseppe Sansone with the HAG in CH4. This is a simulation done by Etienne Plessia in Madrid. If you align molecules, as Professor Stapelfeld described in detail in his first lecture, you have a much richer angular distribution, ideally up to the so-called MF paths, if you detect ions in coincidence, and that those again give you an additional information, a handle to disentangle things. These are very difficult experiments, but they are currently pursued. Okay, now let me go to some correlation effects. Okay, this curious molecule is epichlorohydrin. We were interested because it's chiral and we studied chirality in photoemission. But just here we look at angular distribution and cross-section. Actually, I will just concentrate on those two panels, which are the angular distribution relative to the two central ionization here, which are a bit difficult to disentangle experimentally. And what is interesting is that they both present an undulation here, which is due to a Cooper minimum associated with the chlorine atom. And our first calculation employed DFT and is the blue one. We get the well, it's a bit shifted in energy, but the interesting thing is that the depth well is larger here than here, which is opposite to the experiment. Okay, if we do PD DFT is the yellow one. Now, say the initial part is perfect, the position of the minimum is perfect, but still the depth is higher here, sorry, than here. However, if we use Dyson orbitals, very correlated, thanks to Torsha and Sonia at DTU, you can immediately see that, say, the well depth becomes lower here and higher here. The green is DFT with Dyson, but still has a problem with the minimum. And the red is TD, DFT with Dyson, which fits very well the experiment. Now, this is a parent similar molecule, and this is the chiral parameter that you measure in photoelectron circular dichroism. I don't want to discuss, but just to say that even our DFT description is quite reasonable, quite reasonable. This actually is one of the best agreements we ever got. But I wanted to go on to this more complicated molecule, which is this cobalt surrounded by 3 acetylacetonate ligands, which our colleagues were interested some years ago, because of course, say, molecules containing transition atoms, metal transition atoms, are quite interesting for many aspects. And by the way, they are characterized by a well-known large resonance at a relatively high energy, which is an autoionization due to excitation from a metal 3p field orbital to empty d orbitals. And by the way, say, the chiral effects typically dies very quickly with the increasing kinetic energy. So it was a problem to see if it could be seen in this region. Okay, say, this is the chiral contribution. There are 2 resonances at low energies. This is again the calculated and the experimental. And okay, I would say the agreement is as good as we could hope. So this is fine. And also at the resonance, you can detect the chirality, and again, the agreement is reasonable. And they measure also the cross sections in this region. You can see the Fano profile, again, reasonable. Then a little later, they consider also ionization from the deeper orbitals. And here the theory varies from quite poor to catastrophic. For instance, you can see here or here is completely different. At the time, we just say raised our hands and surrender. We didn't know what to do. Now I'm taking up again, but I don't have results yet. There will be an experiment already scheduled at the Soleil beginning of the year. If you look at the photoelectron spectrum, and here KS are the eigenvalues of DFT that we used for the simulation. And you can see HOMO is reasonable, but then the structure doesn't really fit well the spectrum. And by the way, there is a green function approach, a perturbative one, which was devised by Sederbaum long ago, and it's freely available in the Gaussian program, for instance, and works very well for outer ionization in organic molecule, mostly pretty accurate. So I try to run it here, but you can see it's a total disaster. You have two ionization here, the next here, and so on. Of course, this is not a critique of the approach, which is a very sound approach, just that even in closed shell transition metal atoms, situation is quite complicated and requires a very high level correlated approach for the bound state. I hope that our colleagues at BTU will be able to deal with it properly. Okay, I'll skip this, but I say that in transition molecules, this is common. And by the way, recently we were involved in a study of this object, which is like the previous, but with the additional complication that it is an open shell. And it was a total nightmare. Even with CAS-SCF, we couldn't get a decent reproduction of the experimental spectrum. So we managed somehow with DFT, but I wouldn't recommend. However, anything gets published at last, so it has been just accepted in PCCP. Okay, in the last minute, I would say something on the solution of the time-dependent Schrödinger equation at this level. Say, if we stay at DFT, the total Hamiltonian is a sum of one particle con-sham Hamiltonians here. And if you add the coupling with the field, it's still one particle, so the total Hamiltonian field dependent is one particle. And then it's easy to show that the propagation of the initial Slater determinant stays a single Slater determinants in which the orbitals are individually propagated. So now the complexity of the calculation reduces enormously. Apart from this drastic, if you want, mean field approximation, all the rest is rigorous. And in fact, we verified that the gauge independent, for instance, is accurately verified. Now, there is a second problem when you run a wave packet calculation, that at the end, you want to analyze your wave packet because the detectors detect free field states. But that is not a problem in this approach, because if you think of the cross-section, the differential cross-section in one photon is just this transition matrix element from the initial state to the final continuum through the dipole, but you can just say that you have an initial wave packet and you project it on the final states. So whichever way you excite your wave packet, at the end you have just to project with the final continuum state, but we have the continuum states. So this is not an additional problem. Okay, I will just go very quickly through two examples. One is HHG. It was computed by Marco a few years ago. The problem was the so-called dynamic minimum in the HHG emission. Say there was a minimum which changed with the increasing intensity of the field. He used ADC1, which is a little more than single excitation CI, and could reproduce perfectly the shift in the minimum. If he, say, suppressed interchannel coupling, the minimum shifted to lower harmonics, and the dipole coupling didn't make any special change. And you can see here the computed harmonic spectrum and the minima, and the behavior of the amplitudes along the series of harmonics. Let me just say that, okay, there is a shift, no, in the minimum, but if you are interested in the large scale figure, okay, it's not dramatically different. That means that if you don't aim at very high accuracy, but just to getting the physics, even lower level approaches may work. And this we repeated with our poor man's DFT, and again got, say, a similar behavior of the spectra, but our minima were moved back like in his without, so say, interchannel coupling has an effect to move the minimum. Well, at this level, however, doing water or even C60 is not computationally very different. What impact our calculation is, if you want, the symmetry, the largest the symmetry, the cheapest the calculation. So it's easy to repeat also calculations for many geometries or many orientations. And okay, this is just an example on pyrazine. The change with the change in intensities and with the orientation of the polarization. The green is a polarization along the pi orbitals, and always gives the longest, say, tail. But here, for instance, is the difference between polarization in the plane of the molecule along the nitrogen Z or perpendicular, and you can see that there are some clear distinctions, so it fills the orientation of the molecule. My last example is about ionization. This is again an old one of our first results done in collaboration with Alejandro Sainz in Berlin, Humboldt. And okay, this is ionization. The red is HOMO, the blue is HOMO -1 for various intensities of the field and various orientation. Say the HOMO always dominates with the field parallel to it. In our geometry it was Y, but the HOMO -1 can become competitive if the field is oriented along it, which is Z. So this is the molecule. Actually, this problem has been considered recently also by the R matrix people, Jimena and collaborators, and they found that while in this case, well, say, of course, with the higher level R matrix the profiles are a bit changed, a bit or more, but I say the basics here is that in the plane of the molecule, the HOMO -1 can become dominant, not that much, but dominant. Here, however, interchannel coupling changes very strongly the behavior, in the sense that HOMO is fine, but HOMO -1, because of coupling with HOMO, also have emission strongest along the y-axis. Just to say that
Piero, you have a few minutes more only.
Yes, I'm basically done. Thank you, Torsha. We can reconstruct the full photoelectron spectra, and we could also do the angular analysis of the electron emission. This is water for HOMO with increasing intensities, and you can see going from 10 to the 14, you still have a neat multi-photon, say, pattern, but when intensity goes up, it becomes more complicated because of scattering that has been discussed in previous talk. We can compute it in a convergent way. Just to show you the convergence, this is for rather high intensity for 3 different size of our boxes, which then becomes pretty large. If you want to contain the wave packet, be sure that it doesn't hit the outer boundary. And if you look here at the lower energy, lower electron energy range, you see that 300 is still small. It goes around, but gives a lot of spurious spikes and then goes astray quickly. 600 removes them, and it's quite good up to say around here, 0.6 atomic units, and 1000 is completely convergent over this energy range. Okay, this was just methods. Say that this has been used by other groups with which I have collaborated over the years. For instance, to study PAM-probe in attosecond, rabbit experiments, and so on. But this is, say, in a way, I collaborated, but was their work. So let me just acknowledge collaboration with my historical ex-students, now permanent in Trieste, Mauro Stener and Daniele Toffoli, and other people. And a great collaboration I really loved with Madrid, Berlin, Zagreb, and you can read. I like that very much because it allowed me to explore a lot of things that I couldn't have dreamed to do by myself. We are a very tiny group in Trieste. Okay, thank you very much.
Thank you, Piero, for this wonderful talk. Now, I request the audience, if they have questions, you can both raise your hand and then unmute yourself and ask the question, or you can also write in the chat box. But I think it's a bit more natural if you unmute and ask the questions directly to Piero. Okay, there is a question already from Felipe Zapata. So.
Hello, ciao, Piero.
Hi, ciao.
Very nice talk. Thank you so much. I have a question concerning the method you use to compute the HEJ in CO2. It is also following this independent particle approximation, like the orbitals are also evolving in time, or because now I'm confused about the methods which is the difference, Piero, between the this diagrammatic method, or you call
diagrammatic? Okay, say is the say is like in your matrix. Say depends the level of correlation in the bound states, but say again in say this ADC approach by Marco, there is coupling between the different ionic channels, no? That in our independent particle propagation we lack. No, we have the dipole coupling, which is less important, but the electron-electron coupling between different channels is missing. So this is a real, say, advancement, if we want. Say we are looking to do TD-DFT time dependent, and that would be probably close to it. But say that I agree, say the best approach, in my opinion, is close coupling, that you can devise exactly what to couple and what not to include. No? However, there is also, say, a cost issue. But as computers become more and more powerful by the day, probably in the end, that will be the final answer.
Okay, well, thank you.
Well, I don't see any further questions. And with that, as we are also running slightly delayed, I thank Piero again for this wonderful, very informative and quite educational talk. And now we move on to the next speaker. Maybe you can stop sharing. Yes, thank you. The next speaker is Dr. Soumyajit Saha. He's currently a postdoc at the University of Stockholm. He did his PhD from the Indian Institute of Technology, Madras, and his research revolves around ultra-fast physical processes in atomic systems. And today he will be talking about angular anisotropy parameters for photoionization delays. Soumyajit, the floor is yours.
Yes, I'll just share my screen. Is it visible?
Yes,
to all? Okay. Thank you, Torsha, for this beautiful introduction. This is the work that we have done in Stockholm, at Stockholm University in Lund group. We will see a new expression for ionization delay. It is expressed in parametric form using a new set of beta parameters, which are derived. And they are very closely related to the ordinary beta parameters that we have known for long. But now these new beta parameters are complex. We will then see the various sources of angle dependence of ionization delay. Moving on to the very first slide. So the earlier contention about the photoionization was that it is an instantaneous process, that there is no time lag between the two processes, that the light pulse that interacts and the electron that goes out. But experimentalists showed a decade ago that there is a tiny time delay, and that is of the order of attosecond. So this is the least time that has been measured till date. So it needed much attention. And this delay was not only a delay, but sometimes people saw that it is an advancement depending upon the surroundings of the electron and the nature of the potential. So coming to the motivation about this study, the motivation of the motion of electrons in atoms are in attosecond time scale basically. So one needs this attosecond metrology to study electron dynamics in real time scale. aside from interest in time delay as an indicator to electron transition dynamics, since the time delay is derived from the phase of the transition matrix element, it provides one of the most important part about the ionization process, that is the phase. Actually, the magnitude can be obtained from the cross section directly, but this time delay measurement has a direct access to phase of the ionization process in the ionization. So that together can give the complete picture of ionization process. So after scattering, the outgoing electron will asymptotically be described by this expression. It includes the radial part and the angular part. The radial functions are outgoing phase shifted Coulomb waves that asymptotically approach as plane waves. And these two factors you see, that comes basically when the electron approaches towards the center, then it accumulates one phase factor, and when it leaves the cadence center, it accumulates another factor actually. So Wigner expressed long time ago the scattering delay as this, the energy derivative of the phase of the outgoing electron. Now we do photoionization, and if you think about scattering and photoionization, then they are very closely related actually. In both processes, if you think about electron ion scattering, or photoionization, in both processes the outer products are same. So that is why photoionization is often called time half scattering, and they are related via time reversal symmetry. And all the laws which are applicable in scattering are applicable in photoionization process as well. And so we just drop the two factor and we use this expression for photoionization delay. The major delay in photoionization has two components that I will talk about later. One is the Wigner component and one is the measurement induced component. Rabbit is one of the techniques that has been used for measuring the delay. We follow it in our theory as well. So in rabbit, ionization process is initiated by an XUV pulse, and then these side bands are created depending upon absorption of an IR pulse or emission of an IR pulse in the continuum. So it is basically a process that involves two photons, one XUV and one IR. And then you can see that any one particular state we can reach by two different paths, and that gives rise to interference. And to observe interference, we change the delay between the XUV and the IR pulses, and we get sideband intensity by adding the amplitude and taking the square of them. That is the amplitude of the emission path and amplitude of the absorption path. And when we break this, then we will have the square terms and we will have the cross terms, and that gives this cosine term, and this is basically the term that gives the that basically from this term we get three quantities. One is this quantity which is controlled manually, that is the delay between the XUV and IR pulse. This is the group delay of the XUV pulse that can be eliminated by doing relative measurement. That is when you do a measurement from say neon 2s and from neon 2p, then we can eliminate that by relative measurement. And this is the term that comes from the phase of the different quantum paths. So that path basically gives the delay. Now coming to the angle dependence of photoionization delay. So photoionization time delay is in general anisotropic. From a particular state, if you think about two transitions, then interplay between those two transitions give angle dependence. So for ionization from spherically symmetric s orbital, you can think about non-relativistic transition and relativistic transition. So in non-relativistic case, you will have only s to p transition. That is possible. So you will have only one transition, so you will have no angle dependence in one photon case. But in two photon case, from p to again you can have a transition to d or s. So you will have angle dependence in two photon non-relativistic study. But in relativistic case, in the one photon level, you are having two transitions, that is s to p half and p3 half. So angle dependence will be present in one photon level and also in two photon levels, of course. Here some of the results which are available related to angle dependent study from in the literature. I have shown them here. So this is from Ursula Keller's group, and they showed that angle relative time delay measurement, that is the delay measured in a particular angle, and then relative to that they measured the delays in other angles, and we can clearly see that they vary for different angles. And this is actually measurable atomic delay that was plotted, and this is the only the one photon level Wigner delay that also shows the angle dependence in the Cooper minimum region. Cooper minimum region is the region where cross section or the amplitude goes to minimum, and that changes phase. That has a that changes the phase very abruptly. So here I will not go into the details about how we got the beta parameters, new beta parameters, but I'll just say a few things. So when you think about one path transition, then the differential cross section has been written in this parametric form for decades, and this gives the angular dependence actually. So this sigma naught, sigma total is basically the total cross section integrated over all angles, and in rabbit you will have this beta up to 4. So you will have beta 2 and beta 4. After absorption of 2 photons, the photoelectron wave function will asymptotically be written as this. The M is now the 2 photon matrix element, and this is the plane wave part, and this is the phase which includes the Coulomb phase as well as an additional phase which comes from the short range interaction. And then you have the angular part. Now amplitude which governs the amplitude which governs the angular dependence, from here we get this is the amplitude, and then if we take the amplitude square, then this plane part, simple part of the plane wave will not contribute in amplitude square, as that will be same for all electrons which reach at same state, but this phase will be there as it is different for different angular momentum channels. And breaking this further, we will get this cross term actually, and this phase will survive in this cross term. And if we just express this little further, we will get very similar expression as the parametric form of the cross section. And now moving to the rabbit process. In rabbit, if we think about the square of the amplitude, then we will have square of the absorption plus emission amplitude, and you will get a very similar term as it is there in case of cross section, but it will be complex conjugate of quantity within this bracket and then this quantity, while one will have the M as the absorption M and one will have the M as emission M. And then we will get this quantity, this cross term, and then similarly for this cross term, we will just do it reversely and take the complex conjugate of this and multiply it with this.
Shoma,
and
we have a few more minutes.
Yeah, and dealing with okay, and from here we will get by some further calculations a very similar term like we got in cross section, and taking the argument of both sides as we do to obtain the time delay, we will get this new expression of delay, where this is the total delay measured in a particular angle, and that is expressed as a sum of the integrated time delay, that is the delay for electrons collected in all angles, plus this angle dependent delay. So this is the angle dependent delay that we will focus about in our result section. And here we have plotted the difference between the delay measured in a particular angle minus the delay that is integrated over all angles. So we have just plotted here the angle dependent part of the total delay, and for krypton 4s and for xenon 5s. And we can clearly see that angle dependence is present at low energy region and also in the region of Cooper minimum. But moving on, we will see the same result for one photon level, and that is for the Wigner delay. And we can clearly see that for Wigner delay, the angle dependence is present in only Cooper minimum region in krypton and xenon, and not in the low energy region. So we can clearly say that if we just go back, the angle dependence that is present here is purely coming from the one photon level, and that is from the relativistic interactions. So this is the angle dependence that comes from second photon and not from the one photon level. And we can see that in our third slide of the result section. And here I have plotted the difference between the earlier two delays, that is the total atomic delay and the Wigner delay. And we can clearly see that this is basically related to, we can say that this is a CC delay, the measurement induced delay. And we can clearly see that the angle dependence is present only at low energy region in both cases. And we can also see that they are very similar in magnitude, though the scales are different. So we can clearly conclude about this is a non-relative, conclude that it is a non-relativistic phenomena and coming from second photon. And this delay is universal delay, that is the measurement induced delay, and that has been studied for a long time now, that it is very much universal for all the systems. And we have also shown that here in our work that for krypton 4s or xenon 5s, for almost 10 electron volt energy, the CC delay is very same for krypton and xenon, and also match with the analytical CC results. And only at higher angles, say 70 degree, they shift from the analytical result, but still the results for krypton and xenon follow each other, and only at very large angle they have a specific element, specific behavior actually. And here we have shown the angle relative delay to establish the fact that CC delay is universal. And we can clearly see that when we plot the delay in a particular given angle minus the delay towards 0 degree, so we are basically subtracting the contribution from the CC delay. And we have done that for atomic delay and also for the Wigner delay. And you can clearly see that up to 60 degree, quite large angle, the atomic and Wigner delay are very similar to each other. So the contribution that has been subtracted, that is, we can say that that is universal actually. So, and that is true for krypton and xenon both. And coming to the conclusion, measurable time delay has been expressed in a parameterized form using new complex beta parameters. And we have seen that significant angular dependence is present in Cooper minimum region, and that is because of the one photon level relativistic interactions, and the angle dependence that is present at the low energy region, that is clearly an effect of the second photon, and that is coming from the two photon process actually. And with that, I would like to thank the organizers, and thank you everyone.
Thank you very much for this wonderful presentation. Again, I request the floor is now open for discussion, so anybody can unmute and ask questions, and even also write in the chat box. In the meanwhile, I have a very short question. So you have been mostly focusing on atomic systems. Is this also something that you can do for molecular systems? Because often for small molecules, we have seen that some atomic kind of behavior is also observable.
Thank you for this question. The time delay studies in molecular systems have been performed for a long time now, actually, and we have seen the some of the very good results related to the molecular time in molecular systems and the delay in molecular systems. And this is a new study that we have done. This is that we have expressed the time delay in complex beta, in terms of complex beta. So yeah, we can think about it to extend it to the molecular systems, actually, because molecular time delay studies have been people are doing it for a long time actually now, so you can think about it, of course.
Well, thank you for the answer, and I don't see any further questions. So thank you again for this wonderful presentation.
Thank you so much.
And so we move on to the next speaker, and that is Dr. Felipe Zapata from the Lund University, and he did his PhD from Sorbonne University in France, and after that he was a postdoc at the Mathematical Physics Division at Lund University in the group of Jan Marcus Dahlström, and he works in the field of relativistic effects in many-body attosecond physics. And today he will be talking on the implementation on the relativistic time-dependent configuration interaction singles method, the case of atomic photoionization cross-sections. I see you are already ready. Thank you, and the floor is yours.
Thank you so much, Torsha, for your presentation. Good morning, everybody. I would like to thank also the rest of the organizers for giving me the opportunity to present my work today here. So the work I'm going to present is, in fact, the result of a strong collaboration with a group of Eva Lindroth at the Stockholm University, in particular with Anton, Eva's PhD student, and Jimmy, which is between Stockholm and Lund. In fact, before I started my job in Lund, Jimmy and Eva developed a many-body relativistic code where the source orbitals were computed at the Dirac-Fock level. So in the last year, my work consisted to extend this code to the time domain in order to explore the electron dynamics under the influence of a time-dependent electric field. So today I'm going to present the relativistic time-dependent configuration interaction singles method. And so I tried to do a pedagogical presentation oriented to the young audience and to those who are not so familiar with theoretical simulations. The context of our development is attosecond transient absorption spectroscopy. Normally, this technique is used to study electron coherence and motion in atoms and molecules. Typically, an intense laser field is used to prepare an electron wave package in a coherent superposition of states, while an XUV photon is used to prove the dynamics. In transient absorption, the target quantity is the exchange energy between the total electric field and the target atom. A major contribution to the field of attosecond physics or attosecond chemistry was the experiment carried out by Makis sorry, in 2010, where a complete characterization of the motion of valence electrons in krypton was achieved by means of attosecond transient absorption theory. Since then, attosecond transient absorption have been used in many scenarios, and you can easily find general reviews on experimental and theoretical transient absorption spectroscopy. However, all studies so far are based on non-relativistic transient absorption theory. Although the importance of the spin-orbit coupling, for example, was established already by the first attosecond experiment on krypton. So, regarding the lack of a relativistic theory that can handle strong fields far beyond the perturbative regime, our goal is to develop a relativistic attosecond transient absorption method to study heavy elements beyond the perturbation regime. So for that reason, we decided to first derive our own relativistic transient absorption theory based on the time-dependent Dirac equation within the dipole approximation. Our relativistic theory has been already presented in the second Attochem working group, and the presentation can be visualized on YouTube, and this is the reference to our paper. The derivation of the relativistic instantaneous power, which is needed to compute the exchange energy between the laser and the atom, begins with the time-dependent Dirac equation. And within the dipole approximation, the interaction with the laser field can be expressed in the length form or in the velocity form. Therefore, after the derivation of the time-dependent expectation value of the Hamiltonian and the integration of the instantaneous power, the frequency resolved energy gain by the atom can be given in the length form or in the velocity form. And these quantities are used to compute the relativistic transient absorption spectrum and are gauged invariant. Similar results are obtained if we use the length form or the velocity form. The expression for the length form is similar to the non-relativistic expression. However, the velocity expression is different in comparison with the non-relativistic, because you can see here alpha z is the omega. This is the Fourier transform of the time-dependent expectation value of the z component of the alpha Dirac matrix. And here A of omega is the Fourier transform of the vector potential. So after the derivation of these relativistic transient absorption equations, an important question that we stressed in our paper was about the limits of our theory. In principle, the limits will define the domain of physical phenomena that we can explore within our theory. So generally speaking, the applicability of our theory is controlled mostly by two parameters. The first one is the atomic nuclear charge, and the second is the strength of the laser field that we use to irradiate the system. From a general point of view, the line that you can see here represents together the nuclear charge and the laser strength. In one side of this picture or representation, we have the non-relativistic limit of our theory, where atoms have a low nuclear charge and the laser is weak. On the other side, we are in the domain of the heavy ion relativistic collisions, where effective nuclear charges are huge. It is also the domain of interaction with ultra-strong laser fields that polarize the vacuum. So our theory is restricted to this region, intermediate region between these two limits, where we assume the dipole approximations and also the non-pair approximations, as the pair creation, the positron-electron pair creations, is out of reach. We are not interested in, for the moment, in the creation of positron and electron. So the non-pair approximations is assumed. You can find the validation of our theory in our paper, and once our theory has been validated, The second step is concerns the resolution of the many electron time-dependent Dirac equation. And in this talk today, I will present the approximations and the techniques that we are using to solve this complex problem in order to explore many electron atoms, such as krypton or xenon, under the influence of a strong laser field. So I will present the derivation of the RTDCIS method together with some calculations that show the strength and the limits of our method. And for example, one of the major strengths of RTDCIS is, for example, the inclusion of the spin orbit effect without the necessity of introducing a Haddock potential to the Hamiltonian. As a consequence, we have the direct access to the fine structure of the atomic spectra. So let's start with the derivation of RTDCIS. This derivation starts from the time-dependent Dirac equation, written here in its Schrödinger-like form, where C of t is the time-dependent main electron wave function, and H of t is the time-dependent Hamiltonian. The time-dependent configuration interaction singles approximation consists on describing the time-dependent main electron wave function as a superposition of the single excited state configurations and the Dirac Fock ground state. And the relativistic single excited configurations are created by taking the Dirac Fock ground state as the reference. So an electron is annihilated from a core shell while a particle is created in the so-called virtual orbitals. Here and in the following, the indices A, B, C, and D represent occupied orbitals or holes. P, Q, R, and S, virtual orbitals or particles, and E, G, K, L are used for general orbital indices. The one particle orbitals that we are discussing are given by the Dirac Fock orbitals, which are expressed as 4-component spinors. A 4-component spinor is composed by radial parts and spin angular parts. The P, this capital P, is what we call the large component, and the Q is what we call the small radial component. And here, those are the spin angular parts. A 4-component spinor is characterized by 5 quantum numbers. And here in this in the relativistic theory, kappa is an important quantum number because it relates the total angular momenta J with the orbital angular momenta L. If we focus now our attention on the relativistic time-dependent Hamiltonian I showed you before, it can be decomposed into a field-free part and the interaction term. The field-free part, which is shifted by the Dirac-Fock ground state energy, is given in second quantization by the Dirac-Coulomb Hamiltonian. The one electron operator is given by the Dirac operator, where C is the speed of light, alpha is the alpha and beta are the Dirac matrices, P is the electron momentum operator, and Z over R is the interaction with the nucleus and is given by the Coulomb potential. But the denomination of Dirac-Coulomb comes from the fact that the electron-electron interaction is given by the Coulomb potential, which is represented by the 2 electron integrals here. For the moment, in our implementation, retardation effects are neglected. So the braid interaction has not been used. And as we are going to see, for big elements, those effects may play an important role. So finally, the time-dependent interaction from a linearly polarized laser field is described within the dipole approximation using the length gauge. Here, where Z is the Z component of the electron position operator. And the time-dependent electric field is given by this expression, where F is a shape function. So now we have well described the equations. What we can do is insert the wave function into the time-dependent Dirac equation and projecting on the left with the corresponding configurations. And then we arrive to the equation of motions for the time-dependent coefficients. From these equations, we can see that this method is not a simple single active electron model. As you can see, we have couplings between different ionization channels through the electron-electron Coulomb interaction, which is given here. We note that our equation of motions are in fact identical to the non-relativistic equation of motion derived by Greenman et al. In 2010 in Robin-Sandstra's group. And the difference between the non-relativistic and our relativistic method is the relativistic nature of the one-particle orbitals that we are using here. So let's see very briefly in detail some of the ingredients of our relativistic equation of motion. So for example, one of the most important ingredients is the dipole transition matrix elements, which are derived using the Wigner-Equal theorem and are given here in the length gauge. So as you can see, in the length gauge, we don't have a mix between the large and the small component, and the angular coefficient is going to be derived by the 3G symbols that I'm not going to show you here. Then the relativistic two-electron integrals are expressed using the multipolar expansion, like in the non-relativistic case. However, we have the relativistic Slater integral, which is given here, and this division, this splitting of the integral is really convenient when solving self-consistently the Dirac-Fock equations. I'm not going to stay here longer, so I wanted also to comment on how we obtain the one-particle Dirac-Fock orbitals and the energies. This is by solving the Dirac-Fock equations and in presence of a complex absorbing potential. We use a complex absorbing potential because our simulation is restricted to a simulation box, and during time propagation, reflections may occur at the end of this simulation box. So in order to simulate the real ionization, to absorb these really far ongoing waves, we use this complex absorbing potential to eliminate the possible numerical instabilities. So the cap is only non-zero at what we call the outer region. The problem of the inclusion of the cap is that our problem becomes not Hermitian, and then the inner product is not satisfied. But nevertheless, the symmetry of the complex Hamiltonian that we have allow us to redefine the inner product as a symmetric product. So in practice, you don't take the complex conjugation in the left side vectors. So as a consequence, the matrix elements that we have to compute are complex, and this implies that, for example, an special evaluation for the observables, because observables must be real. So we will define an inner region in this simulation box, an inner region where the observables are real. This problem was also addressed by Greenman et al. In 2010. Finally, another interesting point of solving the Dirac-Fock equations is that as a solution, we obtain what we call the positive energy states, describing the electron, and the negative energy states, describing the positron. The question on how to treat the negative energy state is fascinating, but I don't have time now to discuss all the details. But to sum up, if the positron electron pair creation is out of reach, the non-pair approximation allows us to reject the negative energy state solution from the basis. And this is very interesting because this reduced the dimension of the problem by a factor of 2. So which is something very tempting from a computational point of view. However, as Farry saw in the 50s, when a spectral method is used to evaluate a time-dependent perturbation beyond the lowest order, both the positive and the negative energy states are needed to describe the intermediate virtual states. So, and also it was shown that if the perturbation is described with a non-diagonal operator, which is the case, for example, for the velocity operator, I mean, it's a non-diagonal operator with respect to the small and the large components. These non-diagonal operators will mix the small and the large components. In the case of using this kind of operators to describe the electron transitions, it can be shown that the negative energy states are important, and the contribution from the negative energy states is of the same order of magnitude as the contribution from the positive energy states. But it was shown and studied in these two references here by Bani and Sainz and Celsto, that if we use a diagonal operator with respect to the large and the small component, this is the case of the length operator that I showed you before, the contribution from the negative energy states is greatly suppressed. So this will force us to use the length gauge in the time propagation. So to verify our implementation of RTD3IS, we have explored different observables in krypton and in xenon. As a first validation, we have calculated several energy levels of these two Rydberg series together with their total angular momentum for each energy level. And we have compared our results with NIST and with calculations performed with the Dirac code. Secondly, we have computed the total and partial cross sections with the time-dependent, what we call the time-dependent correlation function method, which is discussed in this reference. And this allows us to compare our RTD3IS method with the well-established relativistic random phase approximation calculations with and without the Tamdan-Kov approximation. And the relativistic random phase approximation calculation were performed by Anton, Eva's PhD student in Stockholm. I'm going not to give here the numerical details, but basically our one particle Dirac-Fock orbitals are represented using B-splines. Here I show you the table for the single excited state energy levels for krypton for these two Rydberg series. I'm not going to enter into too many details because I think the time is, but we see here the energy levels from NIST with the total angular momenta. Then we have the energy levels computed with the Dirac code and with its parity. The Dirac code cannot give us cannot handle symmetry at the CIS levels, but we can get the parity of the level.
Felipe, you have a couple of minutes.
Okay, perfect. So I will then, this is the, well, okay, this is our RCIS results, and this is the comparison between our method, our calculation, with the NIST and with Dirac. And we can say that the comparison is very nice. The difference between our code and Dirac is very small. The comparison, the difference between our code and the results and the experimental results are not so good, but this is because the lack of electron correlation in our method. So here I give you the total photoionization cross sections for krypton. In figure A, we see the calculations with the random phase approximation, with random phase approximation and within the Taman-Koff approximation and RT-DCIS. We see the RT-DCIS overlap with the random phase approximation at the Taman-Koff level, and both calculations overestimate the experimental results, while the random phase approximation matches very well the experimental results. And this is because, in fact, in the relativistic Taman-Koff approximation, what we are doing is we are neglecting what we call the time reverse diagrams. This is the perturbation of the mean field, and we are just considering couplings between frozen hold and particles. And this is what, in fact, we are doing in RT-DCIS. We are not considering the perturbation, the modification of the mean field potential due to the influence of the electric field. But at this level of theory, you can see that we have very good qualitative results that describe the resonances, the decay here, and then the resonance, this giant resonance above the 3D8. Concerning the auto-ionization energy range, we see the apparition of these Fano resonances. However, in these calculations, also with the full random phase approximation, those are not able, if we compare with the experimental here, auto-ionization energy range given by Chan et al., we don't get the correct shape. And this is because of the lack of the 2-electron, 2-hole excitation effects. This is also missing in the full relativist random phase approximation. This is the table for the xenon, and if you have questions, I can show you this table later. And finally, well, with the xenon, we obtain similar results. This is very interesting to see that we are able to get the giant resonance. And well, we have also studied the partial cross-section to explore a little in more details the giant resonance. And well, because we are out of time, if you have any question, we can ask me later. So with the relativistic transient absorption theory plus this method, we are able now to explore, for example, the spin-orbit resolve at a second transient absorption spectra in complex systems. And this is a collaboration that we have already started with a short-term scientific mission granted by the Attochem. So I would like to thank my group in Lund, and particularly Stefanos, who helped me a lot we were discussing a lot on how to run the calculations in IMDEA. So thanks for your attention.
Thank you very much, Felipe. And now we can take only a few questions. So I don't really see anything in any raised hand. Okay, I have a question from Piero. So I unmute you, Piero.
Okay, thank you, Felipe. I just have a curiosity because quite long ago, we tried to use B-splines with the Dirac equation. But because of these, say, negative energy states, it was, say, quite unstable. We just tried to diagonalize the Dirac Hamiltonian. I think I understood from your talk that even at the one particle level, say the basis that you use then in TD CIS, you use the complex absorbing potential. Does it regularize in a way the problem?
Mm-hmm. Exactly. Yeah. We solve the Dirac-Fock equations with the complex absorbing potential. Yeah.
Okay, thank you.
Yeah, thank you very much, Felipe. I don't see any further questions or any raised hand. So with that, we end the first part of the first session, and now it's time for some much deserved coffee break. We meet again in 20 minutes. So it's 11:05 now. So we meet at 11:25.
Okay.
Thank you. We start the second part of the first session. And our next speaker is Francisco Fernández. And he's currently a PhD student in the group of Professor Fernando Martin at the Università Autónoma de Madrid. And today he will be talking on time-resolved images of intramolecular charge transfer in organic molecules.
Okay, so I will share my screen now.
Yes.
Okay, is it working?
Yes, can you go to the presentation?
Yeah, okay. So, well, thank you for your introduction. Well, my presentation is about time-resolved images of intramolecular charge transfer in organic molecules. So the idea behind all this is to study organic molecules with donor and acceptor radicals, such as the paranitronylene molecule, which I present here, where the NH2 radical can act as an electron donor and the NO2 as an electron acceptor. These kind of molecules are molecules of photovoltaic interest. They might be used maybe for solar panels because they can give rise to a charge transfer process upon photoexcitation. So we want to study this photoexcitation process, and this involves ultra-fast electron dynamics. These kind of dynamics have been previously reported in the literature. Here I present the work by Calegari and collaborators, where they studied the charge migration in the phenylalanine molecule. So they studied this process using a pan-probe scheme, where they first ionized the molecule, triggering the charge migration they wanted to study. And then they came with a second laser pulse, whose time delay could be controlled, to further ionize the molecule. And by looking at the fragments of the dication, they retrieved information about the dynamics that were taking place before. So this is a way of tracking the ultra-fast electron dynamics with sub-femtosecond resolution. In our case, what we want to do is to track the coupled electronuclear dynamics, not only the electronic part of the process. So these electronuclear dynamics have been also extensively studied in various cases in the literature. Here I show an example by Cerullo and collaborators, where they studied the excited state decay mechanisms of the pyrimidine nucleosides. So in this example, they have an initial excitation of the molecule, and then they track the coupled electron nuclear motion using transient absorption spectroscopy. And if you see here, they go to larger timescales than Francesca's work. They go to even 1 picosecond. So, well, what we want to do in our case is to kind of combine these two methodologies. We want to study the charge transfer process in this paranitronylene molecule using a pan-probe scheme, which will be as follows. We will start by exciting the molecule with a few femtosecond UV laser pulse, and this excitation will trigger the charge transfer that we want to study. This will ensure the coupled electronuclear dynamics that we have to track, and this will be tracked with a second XUV laser pulse, which will ionize the molecule. And by looking at the photoelectron spectrum of the ejected electron, we will try to retrieve information about the dynamics that were taking place before, so the charge transfer that we want to study. However, this is a long experiment, and so far we have only been able to describe the first parts of it, so the initial excitation and the ensuing coupled electron nuclear dynamics. The ionization is still a work in progress, so in this talk I will present only this initial part. Okay, so the methodology that we used to simulate all this process was the following. We described the electronic structure of our system using CAS-SCF methodology. So we used a 12-10 active space, so 12 active electrons in 10 active orbitals, and we took into account 6 different states of the molecule. We added perturbation theory to describe the dynamic correlation in the system. And we described the coupling with the initial laser, the laser which excites the molecule, in the dipole approximation. Then we described the wave packet, the electronic wave packet, which is created with this initial laser, as a linear combination of eigenstates of the molecule, computed with this methodology that I just mentioned. And we combined these electronic structure calculations with semi-classical trajectories to describe the nuclear motion in our process. These semi-classical trajectories start from a bunch of different initial conditions, which are computed with a Wigner distribution centered around the equilibrium geometry. And then once we have the initial conditions, we propagate them using the surface hopping method, which, as you probably know, propagates the nuclei classically and the electrons quantum mechanically. So, well, the programs that we use for all these calculations were the OpenMolCAS and Bagel codes for the electronic structure calculations. And then to implement the surface hopping method, we use the Shark code. So, well, the results that we obtained for the electronic structure, as I said, were obtained using CAS-SCF methodology. This, as you will probably know, is kind of maybe similar to the CI method, but here we consider the lowest orbitals of the molecule to be inactive, so they always remain fully occupied. There are no excitations in this region. And the highest orbitals are considered to be virtual, so they never get occupied. And the orbitals in between are the active orbitals, and there we consider all the possible excitations. So it's kind of a full CI in this region of the molecular orbitals. So it's very important to carefully select your active space in this kind of calculations. And initially, we wanted to select all the pi cloud of the system and the lone pairs in the molecule. However, this was a 1610 active space, which is very large and it's computationally expensive. And after some test calculations, we found out that these first two molecular orbitals remained always fully occupied. So this meant that we could take them out of the active space, and we ended up with an active space of 12 active electrons in 10 orbitals. And as I said before, we were describing 6 states of the molecule. These 6 states are represented here. This is an energy diagram of these 6 states with the ground and the excited states here. And this color code describes their oscillator strengths. So if you look here, you see that the only state with sufficient oscillator strength to get populated is the 5th one. So if we come with a laser pulse with this shape, this is the energy spectrum of the laser pulse that we are using to excite the molecule, we will only populate this 5th state, and we will therefore have a wave packet composed of the ground state and this 5th excited state. And as a consequence, even if we look simply at the equilibrium geometry, what we can see in the evolution of the density is the following. Here we have subtracted the constant terms in the density to compare with the differences before the pulse excitation. So this is what happens after the pulse excitation and what's moving in this density. So you see that this is an oscillating term, which is precisely this 1,5 cross term of the transition density matrix. This is very reasonable since we have subtracted the constant terms in the density, the 1,1 and 5,5 terms in the case of our wave packet. And so we only have this cross term. And it's a very important cross term because you see that the density around the NO2 radical and the NH2 radical are opposed in sign. So this is a clear sign of the charge transfer process that we are trying to track. So these were just very simple results for the equilibrium geometry. But if we want to describe the nuclear motion, we have to first generate the initial conditions that I was talking about in the beginning. So this is the equilibrium geometry we have. And with the Wigner distributions, we generate all these different geometries with the small displacements. And well, you see that most of these displacements are mainly the hydrogen atoms, which are the lightest ones, so it's very reasonable. And if we now repeat all the electronic structure calculations that we did for the equilibrium geometry for each of these different geometries, we can obtain a semi-classical absorption spectrum of our molecule. This is what I present precisely here. And as you see, the absorption spectrum presents simply one very big peak, which is centered around the same energy of the electronic state in the equilibrium geometry, which was the absorbing one, the 5th one. So it's very reasonable since in the equilibrium geometry, there's only one absorbing state. We only have one absorption peak in in the absorption spectrum, and they are centered around the same energy. So if we now want to propagate the trajectories with the surface hopping method, we have to select a few of them because, well, with this big distribution, we created 5,000 different initial conditions. We can't run them all. It's computationally very expensive. We selected a few of them around this maxima of the absorption peak, was 100 different trajectories. And now I will present 2 examples of the results we obtained with them. So this is the geometry where the trajectory starts, and as time goes by in the simulation, you will see how this geometry is changing. This here indicates the electronic state where the surface hopping propagation is at that moment. In the beginning is the 4th state, and here on the right you will see how the electronic the energy of the different electronic states is changing as time goes by and as the geometry is modified. Again, the surface hopping propagation potential is marked here by these circles. So if you look here on the right, after less than 5 femtoseconds, we already have crossings between electronic states, and we go from the 4th state to the 3rd one. Then we have these oscillations. We change again between electronic states, and toward the end of the simulation, we end up in the 2nd state. And if we look here at the geometry changes in the molecule, you see that most of the motion is just the hydrogen atoms that are moving. But there's an important change here around the NH2 radical, where the molecule starts with the NH2 pyramidalized, but then it tends to planarize as time goes by. This is even clearer in this other example, another trajectory. Here we start from the 5th state, and you see that on the right, the energy of the different electronic states presents again these rapid crossings between states in less than 5 femtoseconds. Here we have a very rapid decay toward the 2nd state, and after less than 20 femtoseconds, we are already in the 2nd state. And here the planarization of the NH2 radical is very, very clear. You can see it here. So these are 2 important results, because the planarization of the NH2 radical indicates that the charge transfer process is taking place. The planarization, okay, the pyramidalization of the NH2, is there in the beginning because the charge is localized around the NH2 radical in the beginning. But then the charge transfer process takes place and the charge moves away from this NH2. So the radical has no longer a reason to be pyramidalized. It tends to planarize, a bit like when you ionize ammonia and it tends to planarize. It's kind of a similar thing. And the other result, which is very important, is this rapid crossings between states before 5 femtoseconds, because this points toward the necessity of the sub-femtosecond resolution that we are using in this experiment to kind of be able to describe these crossings. So this kind of a summary of these 2 trajectories. You can see here on the right the population of the different electronic states, and here the changes in the population between states are very clear. You see that in less than 5 femtoseconds, you have these very rapid changes that I was talking about. So, well, yeah, as conclusions of this talk, it's very important to remark that the charge transfer character of this process is revealed both in the evolution of the density that I showed in the early slides of the talk, and also in this evolution of the geometry of the NH2 radical that we have just talked about. And at the same time, it's very important to point toward the necessity of sub-femtosecond resolution to study these kind of processes, as the crossings between electronic states in the very beginning of the simulation show. So, well, that's all for now. Well, I would like to say that in the future, we want to keep studying these semi-classical trajectories, maybe run topological analysis in all of them, and see how the charge is moving from one side of the molecule to the other. And of course, we have to describe the probing step and the ionization and get our photoelectron spectra. But, well, this is, as you know, not a trivial step, and we'll see in the future. And finally, I wanted to acknowledge the people I work with, Jesus, Alicia, and Fernando, who put up with me every day, our collaborators, Mauro Nisoli's group and Nazario Martin's group, and the funding agencies and projects that made this possible. Thank you.
Thank you very much, Francisco, for this wonderful talk. Now, do we have some questions? I don't see any yet. So in the meanwhile, I just ask you a very brief question. Okay, I see a hand from Tomislav, so maybe he can ask one before.
Torsha, you can go first if you want.
Okay. Okay. So, Francisco, you are the next step, you say, is for the photoelectron spectrum, getting that. What do you intend to use for that? So it's basically is it the R matrix method that you are looking?
Yeah, okay. So we haven't gotten much into that, but discussing with my advisors, we talked about maybe using the XChem code they have here in Madrid, but this molecule is very big, so it might be a problem. So we also discussed about maybe using something like Piero's method with DFT, but I'm still not sure what we are going to do exactly. Okay. So maybe if we can do it with XChem, we will try. I'm not sure.
And how is what you have right now, how is that in comparison to the experimental observations?
There are not experimental observations so far, but we hope that in the future there will be, and we will be able to compare.
Okay, that's very nice. So now, Tomislav.
Okay, thank you, Torsha, and thank you, Francisco, for a really nice talk. I really enjoyed it. I have just a brief question. So you said that you expelled these two pi orbitals from active space because you saw they're always doubly occupied.
Yep.
Yeah, but it's a little bit strange because could you put that slide, if not a problem? Okay, so these are these first two orbitals.
Yes. Yeah.
They're on the site of a molecule where the charge transfer takes place.
Yeah, that's also a striking result for us. But what we saw is that the charge transfer state, the fifth state, that was the one with the highest dipole that I showed here, this one here. We tried to compute this same thing with the 1612 active space, and the charge transfer state was still this one. And it corresponded, and it corresponded to an excitation not from any of these states, which are very low in energy, but from this one to, I think it was
anyway,
this one.
Two orbitals
from here to here, they are not involved here.
Okay, I see.
But yeah, it's very striking. We also thought about that.
Yeah. Okay, thank you.
Well, thank you for the question.
Thank you very much. And now I don't see any further hands or questions in the chat box. So with that, I thank you, Francisco, once again for this wonderful talk.
Well, thank you. I'll stop sharing.
And now we move on to the next speaker, and that's Moritz Heindl. I hope I pronounced the name correctly. And he is a PhD student at the University of Vienna in the group of Professor Leticia Gonzalez. And he works on surface hopping dynamics to entangle ultra-fast non-adiabatic processes, focusing on interaction with laser pulses and the inclusion of intersystem crossing. And today he will be talking on field-induced surface hopping, validation and control. Moritz, you can go ahead.
Thanks a lot for the introduction, and also thanks for putting like this whole conference together and giving a lot of people like me the chance to present the research. And as we've already seen in the previous talk, that one can use this coupled nuclear and electronic dynamics to get some more detailed picture of the actual dynamics that are happening. That's exactly where surface hopping might come in quite handy. And that's why I'm presenting to you like, what are some benefits, what are some downsides, and finally some applications. So first of all, let's start with basic surface hopping. We already got some glimpse of a real application, but here are some fundamentals, like assuming we have a potential using just 3 electronic states like here. Then in real dynamics, we would have our wave packet, and if it's evolving here, it would probably split here and then move independently on the different surfaces. But really simulating this nuclear part of the wave packet is very expensive. Still, this does not hinder people like we've seen before giving talks here to actually do this. But if you want to have it cheaper, so you can go to larger molecules, you can use surface hopping. And what you do is you just approximate this nuclear wave packet that you have initially by a swarm of classical trajectories. And these will then evolve independently and then for their own decide on which surfaces to be propagated on. That's computationally very cheap because we completely neglect all the couplings between all the trajectories. But in doing so, we of course introduce some errors. And what I'm going to present to you now is something that goes beyond the previous talk, because now we explicitly include a laser field into our propagation. And this is more simply done than said, because we just add like all these coupling terms with an external field to our potentials. And that's kind of it. That's everything you have to put in to sufficiently include the laser field. Of course, you could include additional coupling terms going to higher order if you have very strong fields, but essentially this is already enough. Now I'm going to present to you some of the downsides of surface hopping that one commonly encounters that are also present in field-induced surface hopping. And the two that I'm going to present to you are, first of all, the choice of the basis. So here we used our electronic adiabatic basis and then add our coupling terms to our potentials. That's of course a valid choice. That's simple to do. But you could also, in every time step, take now these Hamiltonian containing off-diagonal terms in the potential and diagonalize this one. This time you get a field like a time-dependent basis that's oscillating kind of in the same order of magnitude as the field is. And you have just a different basis in which you could propagate in. Both of these descriptions have their benefits and downsides, and they give slightly different results. Another thing that's a real issue in surface hopping is the overcoherence. And to kind of shortly say what this means, we just again put a new classical trajectory here and think about what's going to happen at this hopping point. Because they said, okay, the classical trajectories are independent, but each of the trajectories kind of tries to mimic the whole electronic wave function. And this would have been split here. So in the real wave packet dynamics, we would have like two different wave packets moving on different surfaces. And kind of the same is happening for surface hopping. So it kind of knows, oh, I should mostly be down there, but some part of the wave packet will stay up there. If you now evolve this trajectory, this upper part wave packet that's always kind of kept in memory, like, I'm partly on this upper surface, is always dragged along. So in the end, our trajectory will always think like, our wave packets are exactly the same place in space, and they can interact with each other. Therefore, surface hopping is inherently overcoherent, which can lead to quite huge errors. There are also some other issues that mostly relate to conservation of the total energy. But the main point I want to bring across here is that there are some issues, and all of these points, you have the option to choose different protocols or options to treat those. And depending on which you choose, you get like different results. This is a bit awkward because you're moving away from a real ab initio dynamic solution to something that's going more and more semi-empirical because you have these different options. And with all this, the question remains like, okay, how good is surface hopping then to treat also this field matter interaction that's also rather complicated and has some quantum implications? And there have been some very recent investigations about this that focus on one-dimensional test systems, checked like one or two of these options, and found that the representation and the decoherence are very important and can lead to smaller or larger errors. With this, I was wondering, like, okay, but how good or bad is this now if I want to simulate like a real molecule, like going beyond one-dimensional test systems? That's the first part of the talk that I'm going to talk about. And secondly, can we then use like the strength of surface hopping of being rather cheap to go for some really huge systems and do some laser control in these systems? Starting off with the first, I had a look at two different test systems, one of them being SO2 and the other 2-thiocytosine. So we go from these one-dimensional test systems to 3D test systems. And for the 2-thiocytosine, we use a reduced dimensionality because we cannot treat all of these nuclear movements at once if we want to have a quantum reference to which we can actually compare whatever I'm doing. Both of these molecules are additionally complicated because they contain a sulfur, which allows for intersystem crossing dynamics. I test a whole range of 36 combinations of various of these protocols or options. And to facilitate this, I cannot really do like on-the-fly calculations for all my molecules, but instead we use linear vibronic coupling potentials that we got from TDDFT calculations. Because then we can also use exactly the same potentials to run MCDDH calculations and really compare to see, oh, how good or bad is our current approach. For this, let's start with SO2, where we just use now a laser pulse of various pulse lengths to excite the population from the ground state into a low-lying valence state. And what we obtain here is something like this, where we first focus on the MCDDH results. So every color is just a different set of dynamics, where just the length of the laser pulse is varied, but the overall intensity of the laser pulse is kept constant. And what we see is that for a very, very short pulse of like 2 femtoseconds full with half maximum, we excite a specific amount of population, and after the laser was acting, the S0 population stays constant. If we go to longer pulse lengths, we see that we kind of converge to what should be excited by this intensity of a pulse, until finally for very long pulses, these are the 2 reddish colors here, we see again that during the dynamics we start to repopulate the S0. And this happens because SO2 is a rather small molecule, so the excited wave packet that gets, for example, excited here, moves around on the excited state surface and re-enters the Frank content region, where it can again interact with the laser pulse, and we get some additional interference terms that lead to this behavior. If we now compare all this to surface hopping using one of these 36 protocols, we see a rather similar picture for short laser lengths, with just a little bit less population being excited. So if we compare this blue line to this blue line, we see there's a small difference, which continues throughout all the different laser pulse lengths. But the surface hopping is like independent, and all the trajectories do not know about each other. We are completely missing this revival of the wave packet or the return in the Frank content region. With this, we could wonder like, okay, maybe for short laser pulses, surface hopping is quite okay. And the question arises, okay, but if I really want to use a long laser pulse, do I need to care about this? And that's something we investigated with the 2-tile cytosine model, where we saw that already in 10 dimensions, we don't see any of these behaviors, because we have so many degrees of freedom along which the excited state wave packet gets redistributed that we don't see a return to the Frank content region in the simulated time. So this was what we got for the S0 population for a single protocol. And what I'm not now going to do is we use all these 36 protocols, setting the full width half maximum to a specific length, and then just get an overview of how good or bad is everything. And because we don't want to look at 36 different graphs here, we just define an error measure, which just calculates the deviation of like, oh, this is our surface hopping population of state 1. This is our MCDDH population of state 1 at time step 20. We do this for all the time steps, we do this for all the states, and then we average across the time steps. If we do this, we get a consistent error measure, and now I'm going to just show you for all the 36 protocols the distribution of errors we obtained. And they look something like this. So our error ranges from 0.26 to 0.46 or something the like, which for you is just a number, but let me tell you that anything that's in this region most of the time is still a very good qualitative agreement. The error calculated with this measure also ranges from 0 to a maximum of 2. Good. What are the most important features now, having tested all these different protocols? It turned out, as has been shown previously, that the decoherence correction is crucial to describe excitation using longer pulses. Longer pulses already meaning 30 femtosecond pulses. And also for all the dynamics occurring afterwards, the decoherence correction is really needed. Additionally, for the strength of the laser pulses used here, it was found that the basis where we keep the interaction with the laser field as off-diagonal terms and on-diagonal terms at the same time is slightly favored than toward, as opposed to the re-diagonalize the whole thing again and have an overall diagonal basis. All in all, there's no perfect set of parameters found in either SO2 or 2-thiocytosine, for which I don't show any results now. But most of all, if you choose a kind of valid or commonly accepted choice of protocols, which includes like, oh, you should take a decoherence correction, then this does not fare like more bad than just standard surface hopping. And with this, I come to the next part of my talk, which is just focused on using surface hopping to calculate and control dynamics that can be controlled in a very huge system. So what's the huge system that we're talking about? So it's a transition metal complex like this, featuring 3 ligands. These are bipyridine ligands, and one of them features this disulfide bridge, which can act as a disulfide dithiol switch and can be used to store like energy equivalents in form of protons or electrons at this new functionality. The interesting thing now is, okay, we moved away from our 3- and 10-dimensional modes to a system that contains more than 160 modes, and we can treat of them all at the same time. While investigating this system with TDDFT, we found that the excited states that are located, or the excited electron is located at the sulfurated ligand, are generally at lower energy than for the bare bipyridine ligands. And the lowest energy triplet state found in the system also is located at this functionality where the sulfur-sulfur bond is increased in the T1 minimum energy structure. The potential energy surfaces can be approximated like this, where we have our 0 state. Here is the path towards the T1 minimum, which is located at one of these sulfurated ligands, so it's blue, and we have our green states at higher energy that are located at the other ligands. And during excited state dynamics, what we will observe is that we have some decay, which finally ends up in this T1 minimum energy structure. This is also something that we saw actually calculating these dynamics now using surface hopping and an explicit laser pulse for the excitation. What we can see here is that here we have the time plotted against the average sulfur-sulfur bond length, which indicates how fast we decay to the T1 minimum structure for all our excited trajectories. And we see that our average starts out as soon as trajectories are excited along this S0 minimum energy equilibrium bond length and tries to converge towards the T1 equilibrium bond length. The idea is now to actually apply pulses to control these dynamics, with the pulses acting already here at this part of the potential energy surfaces before we reach the T1 minimum to excite again to this green band of states, which would not favor sulfur-sulfur bond elongation. And we actually achieved this. Oops. For example, using this train of infrared pulses, where it can be seen that it is possible to keep the sulfur-sulfur bond length at this rather low level. Given that we still or always use some more pulses to keep the population always in these upper excited states, because it's always going to try to go down towards this T1 state. With this, we have shown that you can control the sulfur-sulfur bond length and the decay towards this T1 minimum energy structure using rather simple pulses. And I end up with my conclusion, which on the one hand tried to show that you can use surface hopping using fields to get at least qualitative agreement of what's going to happen in your system. However, it was not possible to find a perfect set of protocols or parameters here. On the other hand, we investigated this control of a huge transition metal complex where simple infrared pulses were shown to already achieve the control to an extent with which we were quite happy. Finally, I thank all the people that have been working together with me in the group of Professor Gonzalez and you for attending and providing some lectures on your own for this symposium.
Thank you very much, Moritz. And it was really a fantastic talk. And now the session is open for further questions. And I have, okay, there's a question from Tomislav.
Hello, Moritz. Thank you very much for really interesting talk. I have like 10 questions, but we surely don't have time for this. Just the most important one. Did you anyhow manage to employ velocity rescaling in the fish? Is it even possible to do? Because you don't have energy conservation, right? And
yes.
Coupling vectors, you just have.
Yeah, so I did like two different things. For the validation step, where I have had these small systems and only used the pulse to excite the population, I used what we have implemented in Shark, which just is a very basic criterion to distinguish between hops that are induced by a laser, where you won't want to rescale the energy because you just take up a photon, you increase the total energy, that's totally fine. And this is just based on, we have the frequency of our laser pulse, which is say 2.5 electron volts. And then if it is within like 0.25 electron volts of this 2.5 electron volts, like the gap that you want to jump in a hop. So if you want to do like a really big hop of 2.5 electron volts, it just assumes, well, this is going to be the laser, because why else would you want to jump 2.5 electron volts? And then it doesn't rescale. So here we actually combined using no rescaling and rescaling then following non-adiabatic dynamics. However, this was not possible for this big transition metal complex where we use this infrared pulse, because the infrared pulse has just a very short amount of energy, which with this criterion would allow all of the hops anyhow. So here we did not use any velocity rescaling at all.
Okay, thank you. Okay, just another more question. If I understood correctly, you have field-induced coupling, but also the, so to say, natural coupling from the molecule. You have vibronic coupling model, right?
Yes.
Okay, so do you think that maybe some part of error originates from the error in the surface hopping due to the intrinsic coupling and not due to the bad description of a field interaction, field molecule interaction? Can you anyhow distinguish between these two sources of error? Because we know that surface hopping is not exact even without pulse. So
yeah, it's a very good question, and I don't know if I can answer it sufficiently, but let me phrase it like this. The beauty that we found in this process of using like the same potentials for both MCDDH and surface hopping was like, okay, any error we include by just using this simple linear vibronic coupling model, well, we have for both our dynamics methods. So here I don't think we include a big source of error compared to the MCDDH reference dynamics. Compared to real experiment, well, there's going to be a difference.
Okay.
And there was another thing that I wanted to say. Let me just give me a
sure
second. Yeah, for the other thing, how to better discern like where these errors are coming from, like MCDDH is not really suited. If you really want to know like why your surface hopping fails at this point of time, you would want to have some trajectory-based method to compare to. So for example, you could use AIMS, which is also trajectory-based and uses classical trajectories, and then you could really see, here it diverges, and then you could deactivate specific couplings to see like, okay, this is now really the case. But
Yes.
with MCDDH, it's kind of weird to say like, okay, my trajectory at this point fails because in MCDDH I have this much population in this excited mode, and I'm like, okay, I don't know.
Yes, yes, yes. Okay, thank you very much.
You're welcome.
I don't see any further questions. So with that, Moritz, I thank you once again for this wonderful talk. And before we proceed, I would like to hand over to Juan Omisti, because I have to leave for some personal reasons. Thanks everybody, all the speakers of the session, once again for their wonderful talks.
Oh, thanks a lot, all the speakers in this session. And now we are taking a lunch break until 2 p.m. I don't know if there is any announcement. I think there is not. So then see you back after the lunch break at 2 p.m.